While in the previous video, we concentrated on the pH of the buffer itself and the reaction of an acid with the buffer, today we're going to look at the reaction of the base with the buffer and see how those calculations are very, very similar, but also just slightly different for what we were looking at before. So we're going to be looking at example 8.3, first of all. We have a half a liter of a buffer where we have oxalic acid and an oxalate ion, and they give us the concentrations of both of those. And the first step is to find out the pH, and then we're going to add sodium hydroxide and see what happens there. Okay, so the first part, finding the pH, is very straightforward. Again, we're just going to be using the Henderson-Hasselbalch equation. So I'm going to have pH equals pKa plus the log of the concentration of the base over the concentration of the acid. Okay, so if I just plug in, all I have to do here, because of what they've given me, I just have to plug in the numbers that they've given me. So the pKa is going to be the negative log of 5.9 times 10 to the minus 2 plus the concentration of the base was 0.750 and the concentration of the acid was 0.150. Okay, gave me concentrations. I don't need moles there. We'll need that in a minute, but right now we just need molarity. So then when I go to solve this, the pKa is going to be 1.23. And then I'm going to add to that, once you divide those two numbers out and take the log, you're going to get 0.133. And then that's going to give me a pH of the buffer of, whoops, I'm sorry. I looked at the wrong number. That's not it. It's not it's not the number that I put there. It's actually 0.699. That looks a little bit better. And then the pH of that is going to be 1.93. So again, not to beat a dead horse, but it is something I want to make sure that you get stuck in your head. The pKa and the pH are relatively close to each other. Now, when I say relatively close, I mean, they're likely within a whole number of each other. It's not like I'm going to have a pKa of 1.2 and we have a pH up around 5 or 6. They're going to be relatively close together. Okay, so the initial pH of the buffer is going to be 1.93. Now, to that, we're going to add sodium hydroxide. Now, when you add sodium hydroxide to a buffer, what's it react with? Well, it's just as the acid reacted with the conjugate base, the base, if you add that to a buffer, is going to react with the acid. So, therefore, this NaOH is going to react with the oxalic acid, H2C2O4 plus NaOH. Anytime you've got a reaction with a strong base or strong acid, we're going to assume it goes to completion. So we're going to donate a hydrogen ion to the OH minus. That's going to separate out in solution. So that's going to give me a water. It's going to give me an oxalate ion. And it's going to give me a sodium ion. Okay? The water obviously is just kind of hanging out because it's in solution anyway. Sodium ion, again, is going to be a spectator ion. But as you can see, I've got both the acid and the conjugate base present. Now, when I use the Henderson-Hasselbalch to calculate the new pH, once I've added the sodium hydroxide, I'm going to have to, in order to calculate what I'm actually going to have left in solution, I'm going to have to go to moles first. And I took the liberty of going ahead and making those calculations over here to the side, just in the interest of time. You can see that in every single instance, what I did is I took a half a liter, which is what they told me the volume of the buffer was, and I multiplied it by the concentration that they gave me to find the number of moles of each one. So I've got 0.0750 moles of acid, I have 0.375 moles of base, and with the sodium hydroxide, they told me I had 20 milliliters of 2.5 molar sodium hydroxide, which is going to give me 0.05 moles of that base. Okay, so in order to do the stoichiometry, I have to have this in moles. So initially, what does my situation look like? So the H2C2O4 is 0.0750 moles, is what I have initially. Initially, I have 0.05 moles of sodium hydroxide, and initially, I have 0.375 moles of the oxalate ion, okay? Again, the water, it's in solution anyway. There's a lot of water there. The sodium ions don't have any kind of effect on the pH, so I'm not worried about them. So these are just the species that I'm worried about. If I assume that this is going to go to completion, so after the reaction is over with, what's my limiting reagent? Well, as you can see, I have less sodium hydroxide than I do of the oxalic acid. So this is going to go to 0. What I'm going to have left here, I'm going to subtract this 0.05. So this is going to give me 0.0250 moles of the acid. And I'm going to add 0.05 moles over here. And so that is going to give me 0.425 moles of the oxalate ion on this side. Okay, so that's how many moles I have. But once again, in order to find the pH, I have to know the concentration. And so again, this is where you've got to kind of keep your, stay on your toes and make sure that you're not confusing molarity with the number of moles. So again, he was really nice to you here. We're still assuming a half a liter of buffer. He says we're gonna neglect the change in volume, which is 20 milliliters. That can be substantial, but he says that we can neglect that. And so what I need to do then is I need to take each one of these and I'm going to say, okay, this is in a half a liter of solution. And so if that's true, then what that's going to do is that's going to give me a 0.0500 molarity for my acid. And for the base, again, if I put that in a half a liter, that's going to give me 0.850 molarity for my base. Okay. All right. Now that I have those concentrations, now I can go back and I can find the new pH. So the pH, I found the pKa from before, which was 1.23. So I'll just bring that down, plus the log of the concentration of the base, which is 0.850, over the concentration of the acid, which is 0.0500. Okay, that's going to give me 1.23, plus when you do that math there, you come up with 0.025, and then your new pH is going to be 3.17. Okay, and so again, you can see that even though we added a decent amount of sodium hydroxide, the pH did go up, but it didn't completely go through the roof because of that buffering system that's available there. Okay, so again, if you learned anything from this particular example, two things here to point out. One is that whenever you're adding that base, it does the same thing as it did with the acid that we did in the example a couple of days ago, where you assume that this reaction is going to go to completion and you've got to use the stoichiometry to figure out how much is left. And then the other thing you have to watch is that you're using concentration and you're not using number of moles. All right. Then we're going to look at example 8.3. And example 8.3 is an example of exactly that type of equation where I can mix a weak acid with a strong base to create a buffer. So, again, we'll look at that and we'll see how that works. Thankfully, this next example is much shorter. So we'll get some more space. Okay, so example 3. I have 450 milliliters of a 4.5 molar solution of hydrofluoric acid, and I'm adding 25 grams of lithium hydroxide. And I want to know what the resulting pH is. Okay, so what reaction is going on here? Well, I have hydrofluoric acid and I have lithium hydroxide, and so because I have a strong base, I'm going to assume a complete reaction. So I'm going to have water, I'm going to have a lithium ion, and I'm going to have a fluoride ion. Okay, where's the acid conjugate base? Well, here's my acid and here's my conjugate base. So here you can see what's happened is that I have used a weak acid, I've added a strong base, and I now have a conjugate base to get into equilibrium with my weak acid, as long as we didn't use too much of this and eat up all of the weak acid that was there. All right, so the hydrogen fluoride, if I'm going to do this, I need to know number of moles. So for my hydrogen fluoride, they told me that I was going to use 450 milliliters, I believe. Yeah, 450 milliliters, so that's 0.4500 liters of a 4.5 molar solution. And when I multiply that out, that's going to give me 2.03 moles. For the lithium hydroxide, they told me that I was going to use 25 grams of that. So I have 25 grams. And a little crazy there. And 1 mole of that, if you use your periodic table, you're going to have 23.9 grams. And so dividing that out is going to give you 1.05 moles. Okay, so now that I know moles, now I can go look at my equation and see what that's going to give me. So I have 2.03 moles here initially, and I have 1.05 moles here initially, and initially I don't have any of that. But at completion, the lithium hydroxide is my limiting reagent, so I'm going to have nothing left down here. When I subtract 1.05 from 2.03, that's going to give me 0.98 moles left of the acid, and I'm going to have 1.05 moles left of the base. Okay, and here once again, I've got 450 milliliters, and so I've got to take that into account when I calculate this. So that's going to be at 450 milliliters, that's going to be 2.2 molar. You're going to divide by the molarity, and when I divide over here, that's going to give me 2.33 molarity. Okay, so again, all I did, take that, convert it to the 450, or divide it by the 450 milliliters that I had there. From there, I can now use Henderson-Hasselbalch. So I have pH. I need the pKa. They gave me the Ka, and that's 7.2 times 10 to the minus 4. Plus the log of the concentration of the base, which is 2.33, over the concentration of the acid, which is 2.2. And so dividing that out, that's going to give me 3.14 plus 0.025. And therefore, the pH is going to come up to be 3.17. Okay, once again, pH is very similar to what I had, because my this amount that it was changed was very, very small because of the nature of a buffer. All right, so we have worked all sorts of different kinds of buffer problems now, and so now I'm going to let you have at it to go back and work some of these other problems where you're going to be concentrating on what happens when you add a base to a buffer, or when you create a buffer by adding a strong base to a weak acid.